Hello and welcome to this lecture, students. So we are discussing the test pattern generation for sequential circuits, and in the last lecture we covered the details of scan based design, and today's topic of discussion is BIST, that is built in self test architecture or built in self test technique. Okay, so what is the motivation to study this particular testing technique is, in case of the scan part design, number of test patterns that generated and test vectors that generated, as we studied in the last lecture, that the number of test patterns were very high, and to store those test patterns we require a large amount of memory. And if we require large amount of memory, then after some time it would become impractical to store that much of data. That storage is not the problem, but the problem is if you have the memory element in the circuit and it requires a lot of data to be stored inside it, then obviously the area overhead increases, the power consumption also increases, and at the same time uh, the task to perform the testing also becomes a little bit complex with those number of test vectors. So various aspects are there why the built-in self-test design was come into existence. Now the other important parameter is, if the circuit itself is capable of testing it, the idea is very critical, the idea is very important. Built-in self-test means you are enabling the circuit to test itself. So you are providing the power, or you are providing the logic of testing the circuit itself. That is nothing but the built-in self-test. Okay, so we will discuss the advantages of this particular approach at the end of this lecture also. Just to have the difference between the scan design and the BIS design, I just I mean I have given you an overview. Okay, so in BIS architecture, you can see the block diagram over here. There are three different entities. First is the pattern generator, second is the CUT. CUT is the abbreviation for circuit under test, and third is the output response compactor. So these are the three things, these are the three main entities. So there would be high hardware pattern generator, and the work of the pattern generator is to create the number of patterns and different test vectors, and then the multiplexer input will be there. So depending upon if we are applying the primary input, it is same as the scan part design, whether we are applying the primary inputs or the pattern that is generated by the hardware pattern generator, it will decide, and the circuit under test will go for the testing. Now this is the primary output, this is the output response compactor. We will see the role of the output response compactor. This is the signature. Signature here means the output that we are getting in the form of the binary. So that binary output will be compared with the comparator, and if the binary output matches with the reference output, this is the reference signal. This is the reference signal which is coming from this particular module. So if it matches with the reference signal, then we will say that it is good, and if it does not match, then we will say it is faulty. Okay, so this test controller will control the hardware and the input multiplexer and the circuit understand and the output response compactor, and also the reference signal generator. Okay, the reference signal module. So this will be under the control of the test controller upon applying the testing signal. Okay, so we will one by one discuss the pattern generator and the output response compactor. CUT is nothing but the circuit under test. Whatever circuit we want to test, that is our CUT. So the two important entities are a pattern generator and the output response compactor. The important point here to mention is BIST cannot test wires and transistors. Okay, so whatever wiring is there, suppose this is the wire, this is the wire. I mean, here you can say that these are the connections, so you cannot relate this with the wires. Wires means you can say that if you are making an IC, then number of wires are there as a VCC ground, and then the supply also in terms of, I mean, interconnecting the different logics together. So those wires cannot be tested. And second thing, the transistors cannot be tested. Okay. Now the hardware pattern generator. What is the hardware pattern generator? The first entity, which is very important. First, patterns cannot be stored in memory. If we do this, as I discussed in the starting as well, in case of the scan part design, there are a lot of test vectors that generates when we apply the scan part technique, but it is too expensive and impractical. If number of inputs are higher, say if number of inputs are 3, then 2 to the power 3 equals to 8 inputs. What about number of input becomes 30, 40, 50, 60, 100, and 2 to the power 100 means, you can imagine how many test sequence and test patterns will be generated, and how expensive that would be to store those number of test patterns. So number of techniques have been developed, and we will discuss the techniques one by one. This is the exhaustive technique. So in exhaustive technique, for n input circuit, it requires 2 to the power n vectors. Again, it is impractical approach for n greater than 20. So if n is lesser than 20, you can still design the exhaustive design for generating the number of test vectors or test patterns. So for a greater number of inputs, the idea is exhaustive. The idea of exhaustive design or exhaustive technique does not that much of use. So we move ahead and we go to the third technique of pseudo exhaustive method. What is pseudo exhaustive method? What was the first method? First method was the scan part design that we discussed in the previous lecture. Okay. So third is the pseudo exhaustive method. Now in pseudo exhaustive method, we do not actually generate the exhaustive test vectors, but it appears as we do it. This is why the name pseudo is given over here. So you are not generating the actual exhaustive test patterns or test vectors, but it appears that you are generating that. Okay, we will see how it will be done. So what are the logics that are behind this particular method? Partitioning the circuit, larger circuit, into the number of sub circuits, or we can say the fan in cones. We will see what is fan in cones. Second is test fan in comes in parallel. Okay. And third is it reduces the number of tests from how this particular figure is coming, that we will discuss after the understanding this example. Okay, I will discuss the other 2 points later. So here you are seeing that two 5-bit counters are there, 5-bit counter 1 and 5-bit counter 2. 2:1 multiplexer is selecting C0 C1 C0 C1. It is connected to both the counters, and first counter is generating the direct output as x1 x2 x3, and here it is x6 x7 x8. And the x4 and x5 is clubbed with x5 through this OR gate, which is coming from 2:1 multiplexer. Now I would say that if I talk about the primary output H and primary output F, this is the fan in cone for primary output H, and this is the fan in cone for primary output F. Why we are saying this? Because x1 to x5, x1 x2 x3 x4 x5, all this logic uh, you know uh, affecting the output of H. Similarly, x4 to x8, x4 x5 x6 x7 x8. Why I am saying this? Because x4 and x5 are common to both the cones. So for H we are having 5 inputs, and for F we are having 5 inputs. So if we have divided it into 2 cones, now the number of test vectors required are 2 to the power 5, because 5 inputs are there. 2 to the power 5 equals to 32. 32 into 2 equals to 64. So reduction of patterns are observed here. Now compare it. So if you see how many inputs are there, the inputs are 8, x1 x2 x3 x4 x5 x6 x7 x8. Now if you go by the exhaustive design or the scan part design that we discussed in the previous lecture, the number of test pattern would be 2 to the power 8 equals to 256. Now here, by dividing the larger circuit into the two parts like this, first cone and second cone, we are actually seeing the effect of 5 inputs only at the single instant, or at the one time duration. So it I would say that 2 to the power 5 equals to 32. And why we are multiplying it by 2? Because we are having the two cones here, or we are having the two sets here. So the number of test patterns that require to test this particular type of circuit is 64. Okay, so this is the idea. Test pattern reduces. Last topic is incomplete fault coverage. Incomplete fault coverage, sometimes you miss some logic because you are not applying it exhaustively. So it may happen that some wire, some connection, or some faults may be left because of not applying the exhaustive logic here. So it is also not practical if we are applying it for n is greater than 50 inputs. So this becomes also impractical. What are the other methods then? So we have seen three methods. All of three are not giving us the satisfactory output. So we are moving to the next method. That is the random pattern generation. Let us see one example here. AND gate, 4 input AND gate is there. Now I want to test this stuck at one. SA1 means stuck at one fault I want to test. So in order to test this, I have to I have to initiate that. I have to I would say the make it enable. So for doing that, I am applying the, or I desire to have the input as 0, because the fault is stuck at 1 and the line is stuck at 1. So if I want to test it, it has to be applied as 0. Okay, so if it is 0, then by using the XORing technique, we will come to know, or we came to know that the fault is. So now we can see that how many test pattern that can be randomly generated. So to have 0 output here, we can apply the input as 0010. We can apply the input as 0001. We can apply it as 0 triple. We can apply it as 00 We can apply it 1100. And number of test patterns can be generated. If 4 inputs are to the power 4, 16 different test patterns can be generated. This is the random test pattern. The number of random test pattern that require are higher. This is the one gate we are talking about. Now see this. Now see this logic. If you are talking about the stuck at 0 fault, and I want to have the logic 1 here, then all the inputs that are applied at the input of the AND gate has to be 1, because I want to test the stuck at 0. So it has to be, if I want to test stuck at 0, the output should be 1. And in order to make the output 1, all the input must be 1, then only the output will become 1 in order to test this particular stuck at 0 fault. So the probability, now if there are 4 input, 2 to the power 4 equal to 16, so the probability to detect the fault, it would be 1 upon 16, because test pattern are randomly generated. So there are 16 possibility according to the inputs. So it may be 1000, it may be 1100, and so on. But in this case, only one logic which is fulfilling the condition is all the 4 inputs must be 1. So the probability to detect this fault is 1 upon 16. Very less possibility. So we may not even detect SA0 there. It may be, because 16 cases are there, and in one cases, only in one case this is fulfilling our need, and in all other 15 cases this particular logic is waste for us. So I can say that we may not even detect the SA0 there. But how would I compare the response if I go by this method only? Suppose if I am applying it for the smaller circuit. But how would I compare the response in case of random test pattern generator? Because test patterns are randomly generated. It is 1000, it is 0011, it is 1000. Any pattern is randomly generated. So how I can compare that pattern with the standard logic? This is again the problem. So now the next method may be the solution for our all the drawbacks and lacunas that we discussed, is the linear feedback shift register, LFSR. It is very popular in case of generating the test patterns. Okay, so here I have shown the example of three different flip-flop shift register. I mean, the shift register containing three flip-flops. So the initial logic is 1 1 1. So if 1 is XOR with 1, I will get 0, and then if 0 is XOR with 1, I will get 1. Okay, and so on. So this will continue and continue. So the next test pattern will be 0 1 1. and the next pattern will be 0 0 1, and accordingly the XORing output and XORing input will be applied, and you will get these much of test patterns. So 7 test patterns are generated. Okay, so standard LFR produces pattern algorithmically. This is the first advantage that we have in case of LFSR. Standard LFSR produces pattern algorithmically. Why we are saying this? Because there is a pattern, there is a certain pattern by which this inputs are shifted, and we are using the XOR gate also. So we are using the shifting property with the XOR gate. So we are generating the test patterns algorithmically. Second, it has most desirable random properties. Okay. Third, we need not to cover all 2 to the power n input combinations. That is also not required. Fourth is it is a long sequence needed for greater fault coverage. Good fault coverage. If you want the fault coverage should be on the higher side, then you have to have longer sequence for test patterns. So other types of RLs are also there, such as generic modular LFSR and so on. I am not going into the details of that. Now our focus will be on primitive polynomials. Very important thing in case of the LFSR. If you want LFSR to generate all possible 2 to the power n minus 1 patterns, then primitive polynomial must be used. So primitive polynomial means the polynomial that can generate the larger number of test sequence possibility. Okay, if we generate, as we have seen in the previous page, if we generate number of test patterns in greater in number, if we generate say if 10 or 20 or 30 or 100, depending upon how much test patterns are required for your circuit. So as high the test pattern will be, your efficiency of testing that particular circuit will be higher. Okay, so that is the primitive polynomial that assure you that ensure that we are going in the right direction and the circuit will be tested on the right sequence. So now the characteristic equation for this is, for polynomial, is fx equals to 1 plus h1 into x plus h2 into x square plus hn minus 1 x to the power n minus 1 plus x to the power n, and so on, like this. Now what is h1, h2 and h? It is a tapping. We will see what is tapping. What are the condition to have this particular primitive polynomial? First condition is coefficient of x to the power n term must be 1, as stated above. We are writing the equation from 1 plus something, so it has to be 1 plus something. The polynomial should have the coefficient as 1. h1, h2 are tapping, as I just told you. Now see, suppose we are talking about this particular logic. So here, if I want to write the polynomial equation for this particular point, first point, and I have to write 1 plus x. Okay, here there is no tapping. If there is no tapping, I will have 0 into x square, 0 into x square, because there is no tapping over here, plus x to x cube for this particular third logic. Okay, so the polynomial will be 1 plus x plus 0 into x square plus x cube equals to 1 plus x cube. So this will be the polynomial. If tapping was there at the second flip-flop, then the equation would be 1 plus x square plus x cube. Okay, but here, since the tapping was not there, then we have written the logic as 1 plus x cube. Now the characteristic polynomial must divide the polynomial. Characteristic polynomial must divide the polynomial 1 plus x to the power k for k 2 to the power n minus 1. This is the second condition. The characteristic, I am repeating, the characteristic polynomial must divide the polynomial 1 plus x to the power k. What is 1 plus x to the power k? Now suppose k is nothing but number of flip-flops that will be required. Okay, so 2 to the power n minus 1, suppose we are having the 3 inputs, so 2 to the power 3 minus 1 equal to 7. Okay, so the idea would be 1 plus x to the power 7. Now if 1 plus x to the power 7 is the idea, now what factors we should have? The factors should be 1 plus x, 1 plus x cube, 1 plus x square plus x cube. Now how these factors have come? Look at this. If we talk about this particular point, this is the h1 point. First factor is 1 plus x. If we talk about this particular point, if the tapping was there, then it would be 1 plus x square plus 1 plus x square plus 1 plus x plus, sorry, 1 plus x square plus x cube. And for this case, if the no tapping was there, it would be 1 plus x cube. Okay, so three possibilities are there. So three, first flip-flop, for second flip-flop, and for third flip-flop. It is written like this. If you have the first flip-flop, you will be having 1 plus x. If no tapping is there, 1 plus x cube at the second flip-flop, and at the third flip-flop, 1 plus x square plus x cube. It is written by the design of this particular figure that is shown over here. Okay, so also since three flip-flops are used here, the mandatory term will be 1 plus x to the power n, that is 1 plus x cube. Now which particular factor is satisfying the idea of 1 plus x to the power 3? 1 plus x is satisfying? No, it is not satisfying. 1 plus x is satisfying? It is not satisfying, because there is no 1 plus x cube. Now 1 plus x cube, here it is having 1 and here it is x cube. Now it is 1 plus x cube. Now 1 plus x square plus x cube, 1 plus x cube is there. So the second and third the factor is providing me the output for the primitive polynomial, and both are the primitive polynomials, and based on this design I can have the tappings like this. Now for the first 1 plus x cube, I have the same logic as drawn in the previous page. Now here at second, 1 plus x square plus x cube, because here we have shifted the tapping to this, so 1 plus x from here, x square from here, and from final x cube. So this is how we can draw the logic for random test pattern, linear feedback shift register with the primitive polynomials. So primitive polynomial means we will have larger number of test sequence if we select 1 plus x cube with the help of second or third logic. So we can design this logic also, and we can design this logic also. Both will be our primitive polynomials, and by having both this design, we will able to have more number of test sequence, and the efficiency of testing the circuit will be higher. Okay. Now the response compaction. Till now we have discussed about the test pattern generation. Okay. Now we will be discussing about the response compaction. What is the problem? First discuss what is the problem or the motivation of having the response compaction. We are compacting the response. Why we are doing this? First is several amount of data of CUT response to LFSR patterns. We have generated so many test sequence, and that has been applied to CUT to test that using the LFSR. Now 5 million patterns generated randomly. CUT has 200 inputs. These are the different cases. Suppose 5 million test patterns were generated. Suppose CUT has 200 inputs. It leads to 5 million into 200 equals to 1 billion bits response. Can you store 1 billion bits response? Even if you can store, it is not economical. It is uneconomical or costly to store, and also the controllability or observability of the response would be very low. So to check these kind of response is not possible. So hence responses must be compacted. Some important terms are there when we are talking about the compaction of the response. We are talking about the compacting the idea of the response. Is first is aliasing, very important. Due to information loss, good signature matches with bad signature. It is same like, suppose you are signing your data in the in the bank, and if any fraud happens, and if any other person is having the same sign as yours, and he or she is taking the undue advantage of that, so it becomes problematic then. So the good signature matches with the bad signature due to the information loss. Maybe the fault is there, but we uh, were unable to detect that fault, and because of that mismatching, because of that information loss, the mismatching is happening. Second is compaction, drastically reduce number of bits in original circuit response, but some information will be lost, and this process is irreversible. So there are two important terms. Second is compaction and third is compression. So instead of compaction, we will go for the compression. Reduce number of bits in original circuit response, no information loss is there, and it is reversible. We can go back and change the logics. Here in case of compaction, we cannot go back. If we have changed the logic, it will be remain changed. Okay, we cannot go back and uh, change that logic again. So compression would be the preferable thing or preferable method. Fourth one is the signature analysis. Actual signature generated during the testing gets compared with the good machine signature. This is the reference signature. Reference signature is compared with the actual signature. If this is matching, you will say the circuit is good. If it is not, then you will say the circuit is faulty. Fifth is the transition count. Count the number of transition. This is the method. Count the number of transition from 0 to 1 and 1 to 0 as a signature. Now we'll see the example. Now this is the one example which is showing the problem in case of the transition count. Now the input of this particular NAND gate is 0 1 0 1 1, and the another input is coming from the another NAND gate. This is having 1 1 1 1 0 and 1 1 0 1 1 as the input, and this is the output. Now suppose the fault is there here at the A. The fault is there here at the A. Now what would happen? So in case of the fault free logic, suppose how this logic is coming, you can bit by bit perform the NANDing operation. This will be there, and this will be uh, NAND with 0 1 0 1 1, and you will be getting the logic as fault free. Stuck at one fault is there, no? So fault free logic and faulty logic, you can apply. You can have the pen and paper, and you can apply the logic. You will be easily getting this logic. This is the simple digital logics and patterns. So there is no need to understand every bits. The idea that is important here to understand is, this is the fault free output and this is the faulty output. Now see the transition from 1 to 0 1, 0 to 1 1, and 1 to 0 3. How many transitions are there? Three transitions are there. Here how many transition is there? 1 to 0, one transition is there. Three transition and one transition for x1. Similarly, this output is connected as input to this. Now the idea of this x2, there will be again two outputs, or either it will be fault free or it will be faulty. Now here you can see that the number of transition from 0 to 1 and 1 to 0 is only 1, in case of fault free as well and in case of faulty as well. So can you check by just having the transition count that your circuit is faulty or not? You cannot, because here for x1 the fault free changes transition are 3, faulty is 1. Here you can check, but here in case of x2, the transition that is happening in case of x2 is 1 for fault free, and for faulty also it is 1. So for x2 there is aliasing effect. The signature is matching. The good and bad signature is matching, so aliasing effect is there. So number of transition in case of x1 is differing in from fault free to faulty, but it is not differing from fault free to faulty in case of x2. So for x2 this transition count method fails. Now how can we do other methods? How can we go ahead? Now the next method is, you can use one XOR gate. Now if you use one XOR gate, suppose two inputs are there with two error inputs are there. So if inputs are odd, if inputs are even, two things are there. So if inputs are odd, aliasing effect will increase. If inputs are even, aliasing effect will reduce. So again the probability would become 1 upon 2, that is the 50%. So only 50% probability is there to test this particular having the aliasing property, checking the aliasing property, sorry. Now the other way is generating the cyclic redundancy check code, that is the CRCC. Very popular. Just as we do in case of the communication system, we are having some pattern in the input. We encode that pattern and we transmit over the medium, and we receive at the output at the receiver. So if both the and the output at the output end or at the receiving end, the same code has been decoded. So if both the codes are matching with each other, then we say that our message is correctly transmitted or received. If not, then the case is opposite, faulty. So treat data bits from circuit primary outputs, PO means primary outputs, to be compacted as decreasing order coefficient polynomial. Again, the polynomial concept is there. So, okay, so CRCC divides the PO polynomial by its characteristic polynomial. Again, CRCC divides the PO polynomial, primary output polynomial, by its characteristic polynomials. So in the process, it leaves remainder of division of LFSR, obviously, and this division must initialize LFSR. Sorry, the LFSR must be initialized. The LFSR must be initialized to seed value before testing. Okay, some initial logic should be there before testing. Now, after testing, we will compare the signature in LFSR to know good to the known good machine. If the signature matches, we will say that the circuit is non-faulty, fault free, and if signature does not match, we will say the circuit is faulty. Let us see an example. LFSR response compactor, an example is there. So now we are having a linear feedback shift register. We are having number of XOR gates connected towards the input of the D flip-flops. Okay, so here one, two, three flip-flops have three XOR gates have been used. We are getting the primary output as x0, x1, x2, x3, and x4. Now the characteristic polynomial that has been given for this particular idea is 1 plus x cube plus x5. You can also calculate 1 plus x, typing is here 1 plus x, then no typing is here, x square is eliminated, then typing is here x cube, and then for entire circuit you can have the x to the power 5. Okay, or maybe there is a fault, there has to be one or one more logic written over here, one flip-flop is missing, I think. So you can imagine that x to the power 5 is coming from there. Okay, now LFSR seed value is for this particular example is 0 0 0 0 0. So we are initializing the LFSR with 0 0 0 0 0. So here you can say x to the power 0, x to the power 1, x to the power 2, x to the power 3, x to the power 4. Inputs initial state is 0 0 0 0 0, and we are applying the logic simulation from 1 0 0 0 and 1 0 1 0. This is the pattern that we are applying for the logic simulation. Okay, now depending upon the XOR inputs, these states are generated. X to the power 0 will be 1, then 0 0 0 0, and then so on. Okay, at the end what we are getting at x to the power 0, we are getting 1 as a remainder. At x to the power square s square, we are getting 1 as remainder, and x cube we are getting 1 as remainder. So we are getting 1 and coefficient of x square and coefficient of x cube. So 1 plus x square plus x cube is the remainder here. So by applying the logic simulation, we are getting the remainder as 1 plus x square plus x cube. Now we will check whether we are getting this particular remainder in case of the division also. So similarly, the polynomial for input sequence can also be written. This is the input sequence. This is the input sequence that has been applied to test. This is the input sequence. Here 0 1 0 1 0 0 0 1. If you remember, in case of the simple LFSR, no inputs can be applied. Okay, but in case of modular LFSR, we can apply some inputs like this to initiate our test pattern. Okay, and so if you write the polynomial for this particular pattern 0 1 0 1 0 0 0 0 1, so simply you can write 0 into x to the power 0 plus 1 into x to the power 1 plus 0 into x to the power 0 x to the x square. So 0 1 0 are the coefficients, and from x to the power 0 to x to the power 7, depending on number of bits that are there. So 7 bits 8 bits are there, so we have written x to the power 0 to x to the power 7. So the input sequence polynomial is coming out as x plus x cube plus x to the power 7. Now we will perform this symbolic polynomial division. So what is the characteristic polynomial that we have written? We have written the characteristic polynomial as 1 plus x to the power 3 plus x to the power 5. Okay. Now we are applying the modular theory, na? We are applying the modular theory and applying the modular logic here for division. Now we have seen that input test sequence is written like this. So input sequence is written like this: x to the power 7 plus x to the power 3 plus x. Now we are dividing it. So when we divide it, we are getting the same remainder, x cube plus x square plus 1, that we have seen in the previous page, x cube plus x square plus 1, or 1 plus x square plus x cube. Okay, so 1 plus x square plus x cube. So remainder matches from logic simulation of the response compactor. So when we are doing the symbolic polynomial division and when we are doing the logic simulation, both the outputs of remainder is matching. So we can say that our compaction is good and circuit is behaving good. Otherwise, we can say that circuit is behaving badly. Now aliasing, we can say in this case, see 2 to the power n upon 2 to the power k. What is n? N is the number of inputs. So 2 to the power n, k is the number of flip-flops. So 2 to the power n upon 2 to the power k. So the probability, how we can calculate it, it would be from this idea, 2 to the power n minus k. Why I have written the minus 1 here? Because minus 1 is showing me one good pattern. At least one good pattern would be there, and upon the total number of patterns, so 2 to the power n minus 1. Okay, so this is the probability equation that by analyzing this particular probability equation, we can come to know about the aliasing. Aliasing, I told you already what is aliasing. Now if n is greater than k, the aliasing will become 2 to the power minus k. So what this 2 to the power minus k is signifying here? It is signifying that if number of inputs are higher, we are actually having the dependency on the number of flip-flops only. So the dependency on number of inputs to calculate the probability of aliasing is eliminated. So this is the favorable condition for us because we are only relying on the number of flip-flops. Okay, so 2 to the power minus k is desirable, favorable condition for us. Now what are the overheads? As we discussed in case of the scan design also, we have to discuss the overheads also here. Now till now whatever things we discussed, that is for the one output only. So for one output, one SISRs, scan register must be 1. So single input scan register, then a single input scan register, and so on. So number of LFSRs will be there. So if number of inputs are there, number of flip-flops are there, the overhead of your circuit will certainly increase. But since LFSR is a linear system, we can apply the superposition theorem and the number of SISR can be combined. So in case of, instead of having number of different SISR, we can have multiple input scan register or the multiple input shift register. So that is known as the MISR. Single MISR we can have, we can apply the superposition. Now the last thing that I want to discuss is transition count versus LFSR. We have seen the case of the transition count and now we are seeing the LFSR. How LFSR is better than the transition count? So in case of the transition count, here we concluded that the case of x2 is not giving us the correct logic. Now we compare that and we will see that how this LFSR is performing good. Now suppose the pattern we applied for 3 input is this, and the responses are good, and then stuck at fault at A, stuck at fault at B, and stuck at fault at F. Now suppose the idea of output is coming like this. Now number of signatures that we are getting from transition count, we are getting 3, 3, 0 and 1, and for LFSR we are getting 0, 0, 1, 1, 0, 1, 0, 0, 1 and 0, 1, 0. Now you can say from this analysis that here we are able to detect no faults in case of transition count, and here we can generate the a pattern for 0, 0, 0, 1 to detect that fault. So obviously LFSR is providing me the output for testing all kinds of possibility and all kinds of faults where transition count is not that efficient. Okay, so what is the summary? Summary is LFSR pattern generator and MISR response compactor are preferred BIST methods. BIST has overheads, test controller, extra circuit, delay, pattern generator, response compactor, DFT to initialize circuit and circuit under test. These are the say the overheads. What are the benefits? First, at speed testing for delay and stacked faults. So stacked faults and delay are tested very smoothly. A drastic ATE cost reduction. Okay, so when you apply the automatic test pattern generation, uh, then also the cost is higher. So cost reduction is there in case of the BIST. Third is it is having the field test capability. Fourth is faster diagnosis during test system. And fifth is less effort to design the testing process. Sixth is shorter test application times. Why less effort? Because we are following some algorithm. And shorter test application times, yes, obviously, because again we are following the polynomial terminology and algorithm. We are having the shorter test application times. So this is all about built-in self-test in detail. And as I said in the previous lecture as well, if you want to study just the theory portion, you can go the 2 lectures back and study the theory portion of VLSI. And if you want to study in detail, go through this lecture. Thank you for watching and listening.